Hey everyone, today we're going to talk about some aromaticity and organic chemistry, and we're going to discuss what aromatic structures are, what makes them aromatic, how to go over and how to name some of these compounds, and also taking a look at common structures that are aromatic that you'll be using throughout the semester. So first off, it's beneficial to talk about a very common structure called benzene. Benzene is aromatic, but just before we get into aromatics, I'd like to take a moment to discuss that benzene, as you can see here, is a 6-carbon ring with 3 double bonds in it, or overlapping p orbitals. Benzene can also be represented by shifting the double bonds, as you can see over here. And it's also represented by a ring with a circle in the middle. So, just throughout this, the rest of your organic chemistry, it's beneficial to note that all these 3 structures are the same thing. They're called benzene. Secondly, I'd like to just point out an alkene from a carbon ring, and a bromine. A little bit of stereoism we get here, showing that this double bond is broken down into an alkane. Recall that the shaded bond means it's coming out towards you, and the dashed bond means it is going out away from you. Now for nomenclature. I've created a list here for aromatic compounds. We start with stereoism. If there's stereoisomerism, that would be identified by if there was a meta, ortho, para, if there was, and that also can be abbreviated to O, M, or P, which we'll discuss in a bit. Then the substituents. Obviously if there's a bromine coming off or an alcohol group, which we have an example down below. And then we go into the rut. The rut would be, we have here, benzene. So benzene is a rut. And then furthermore, if it's unsaturated functional groups, the stereoisomers of that, and then substituents off the following. So substituents off that, and then another rut. Alright. So here, I drew an example. We have a benzene ring. It's called 1-bromo-2-hydroxybenzene. How do we get that? First, I circled the substituents in this light green color. We have bromine and OH. Since bromine is a B, starts with a B, using just normal naming rules, you start with bromine, and then hydroxy, the hydroxyl group, the second. So we got 1-bromo, 2-hydroxy, and then in the blue box, I've highlighted, you see we have a benzene. And that benzene is the rut that would go on the end. Alright. And then down here, we identify that there are more common names. So what we have right up here that is an underline, that is the IUPAC name. And you guys have already seen this, most likely, if you've gone through Organic Chemistry 1. IUPAC name is the widely accepted name. You should always default to that if you're unsure of what your professor wants, or if you're on a test. Always use the IUPAC name. You'll have the answer right if you use that one. Now, then in your labs, you will see that if you're using reactants, they will be named this 2-bromophenol, they'll be named like that. You'll see that inside of the chemical formula, or the chemical formula will most likely be on it, but you'll also see these names. Those names are also represent the same thing. They're not traditional IUPAC, so just make sure your professor's okay with you naming that. I just put it here to make you aware that there are alternate names to the same compounds, and you will be seeing that throughout the semester. Next, I took the time to draw out these structures. These structures you will be using very commonly throughout organic chemistry too, if you haven't used them already. Benzene, obviously, almost every chapter in organic chemistry you will see it. You have toluene, which will be used probably in the Claisen-Schmidt reactions towards the end of your semester. Phenol, obviously you can start seeing that the benzene ring is all there, and then the name just gets altered by what substituent comes off it. So you have the OH group. When you see an ol, right? If you haven't figured this out already, when you see ol, there's gonna be an OH group somewhere. So if you see an ol in an IUPAC name and you don't have an OH in that structure, a good bet is that you have it wrong, and you need to identify where an OH needs to go. All right. And just going through it, feel free to copy this on your own time, pause the video, copy, and maybe try to name yourself. I would say the top half of these structures you will see very more commonly than the bottom half. However, the bottom half becomes more relevant, I would say, towards the end of your semester. But nevertheless, it's a good idea just to be aware of all of them. And then when you're doing naming practice, feel free to come back to this and then see if you can use this to help you out naming. Here I have some examples or example problems we can work on. Take a moment, if you have, to maybe try and solve this on your own. And I'm going to go through them right now, and you can check to see if you got them right. Alright. So what do we have? 4-hydroxy, 3-methoxy, benzaldehyde. I've underlined keywords. You see how we have 4-hydroxy. We identified previously that the hydroxy. Alright. What do we do up here? We have hydroxy up here. Do you see that? Oh, sorry, hydroxy. That was an OH group. So we know there's an OH group, whatever the 4 position is. Okay. We also see a key word over here. Benzaldehyde. But we see benzene. When you see benz, there's probably a benzene in it. So let's just get started by drawing that benzene ring. And remember, it's completely acceptable to draw the benzene ring with the circle in the middle as well. Alright, 4-hydroxy. We have to identify first what is the 1 position. The 1 position, remember, you can make it anything you want on the ring, and you just have to be able to, the rest of the substituents have to be able to follow, okay? Alright, so 4-hydroxy, obviously that's not the first position. 3-methoxy benzaldehyde. Well, what do we have up here? Benzaldehyde. Oh, so if you have benzaldehyde, then you must have what we call a double bond. Alright. So that makes that we've identified our first position. Remember, see, even though we have an H up here, right? You don't need to draw that H. You can if you want. But just note that that's an H. That is not an extra carbon. That's why I've drawn an H there. And if you decide to draw the bond to that hydrogen, make sure to put hydrogen in there, or else you'll have the structure incorrect. Alrighty. Now we have our first position, another benzaldehyde. We have the parent structure, so to speak, or the root structure. Now, what direction should we go? Can we go this way, or should we go this way? Either direction's acceptable as long as you keep it, as long as you do the same from all the structures, as long as you keep it consistent. Alright, so 1, 2, 3, methoxy. Well, when you see oxy, you know that there's oxygen in it. So we're going to have a third position right here. There's going to be an O. We know there's a methyl coming off that oxy. So that is our methoxy group. Okay. So that is done. We have our 3-methoxy benzaldehyde all accounted for. And now we just need our 4-hydroxy. Alright. Remember, starting here, we got 1, 2, 3, and then 4. So our 4 position right here. Draw the 4 inside the bond. Boom. And that is 4-hydroxy 3-methoxy benzaldehyde. Congratulations if you got that right without looking. If you need extra help, that's fine. I would encourage you to do more examples like that. This next one I've chosen is maybe a little bit not as well known. It's but the method is the same. We see the word benzene. I've underlined some key groups. We see methyl, trintro, and benzene. So since we know there's a benzene, we're just going to immediately start by drawing our benzene ring. Alright. 2-methyl 1,3,5 trento. Now, here we go. So, we know there's a 2-methyl, and we know that this benzene is just going to have a ton of substituents off it on the 1, 3, 5, and 2 position. So 1, 2, 3, 5. The 4 position should have none. So we're going to identify the first position right here. Think of it nitro almost. This is going to be, so I think I spelled this wrong, guys. I'm sorry. I was wondering why this should be trinitro. Apologize for the confusion. It's trinitrobenzene. Okay, we see the prefix tri, right? And then we see nitro. So 3 NO2 groups. Alright, so we got 1, first position. The first position is whatever you want to make it. I just make it the top. Some people make it on the second position from this first position I made. That's completely fine. So we got NO2. 1. So we got, let's number this. It's a good practice, especially when structures start getting more complicated, to start numbering your compounds. 1, 2, 3, NO2. 1, 2, 3, 4, 5. Alright. So we have 1, 3, 5 nitro. We just need the 2-methyl. And that's it. If you want to, you can write CH in the end. You don't have to because that's understood. So there's our 2 example problems. Moving on. Now we're moving into aromacity. 3 rules that every aromatic compound must have, and if it does not have it, it is not aromatic. Okay? 1, there must be a ring. Okay? No ring like this. No ring. Not aromatic. The ring must be comprised of continuously overlapping p orbitals. Okay, I've driven out a ring, and then I've driven out p orbitals. Remember, that's like the infinity symbol. That's what they look like. And that ring must contain an odd number pair of electrons. If it is not odd, then it is anti-aromatic, and we will get into that in a bit. All right. Here I have some examples. We have 4. So I wrote this formula. This formula is the best for aromatic. It's also one of the few formulas in organic chemistry. 4, 9 plus 2. Simple algebra. It just helps you solve if you have an aromatic compound or not. So here we see we have 0. So we have 0 pair of electrons. All right, 4 times 0, obviously I drew it out up here. 0, 0 plus 2, that equals 2 electrons. Okay, 2 electrons. All right, it takes 2 electrons to make 1 pair. So if we only have 2 electrons, we have 1 pair. All right, now next one. N equals 1. 4 times 1 is 4, plus 2, that gives us 6, obviously. You need 2 electrons in each pair. 6 divided by 2 equals 3 pairs. Odd number, aromatic. N equals 2. 4 times 2 is 8, plus 2, we got the 10. Divided by our 2 down here, that gives us 5 pairs. 5 is an odd number, aromatic. So, boom, aromatic. N equals 3. 4 times 3, 12. Plus 2, 14. Divided by 2, we get 7 pairs. 7 is an odd number, aromatic. And you can go on and on and on. What if we do N equals 4? So we do 4. It's 4. Alright, we get 16. Plus 2. Alright. 16 plus 2, 18. 18 divided by 2, we get, 18 divided by 2 is 9 pairs. Aromatic, odd number, boom. Okay. What if there's an even number? And we identify this. I'll do the structure out here, the square structure, right? We have 2 bonds in there. One of the easy ways to count a pairs is just to count the number when you see a double bond. So like here. Alright, here's our benzene. Alright, see double bond right here? 1, 2, 3. 3 pairs. That would be aromatic. We get that right there. What if we have the square-like structure right here? What do we do then? Okay, so that is not aromatic, right? But this might be confusing because this passes the first 2 of the criteria. We have a ring, yes we do. We have continuously overlapping p orbitals, yes we do. Do we have an odd number? No, we do not. We have 2. And it might be confusing because you're like, oh, there's 2 pairs up here, or 2 up here. Don't confuse this N equals 2 up here with that being the number of pairs. So we count our 2 pairs. We use the formula 4n. Right here, sorry. Use the formula 4n. Okay? 4 times whatever number of pairs you have in there. That's going to give us our anti-aromatic. So we got 2. So we're going to do our 4. Let's do the structure up here. Times 2. Alright. equals 8. Alright. Now we have divided by 2 because there's 2 electrons in each pair. It gives us 4, an even number. Alright. So since we have an even number, that means it's anti-aromatic. So with any even number, we get aromatic. So when you see an odd number pair of electrons in a ring, it's probably aromatic. And when you see even number, it's going to be anti-aromatic. All right. Let's do some examples. Do benzene again. All right. I'm going to draw it kind of coming out at us, or trying to draw it flat. So you can see the p orbitals better. I don't know if this is better, but no, we're just gonna get rid of this. You can see that I was trying to do 3D, but you guys can see. Same structure. I'm gonna draw this in purple. There are p orbitals. Okay. Ring, yes. P orbital is overlapping continuously, yes. How many do we have? All right. 1. That was a bad one. 1, 2, 3, 4, 5, 6. 6 electrons. Divided by 2, 3 pairs. The structure, aromatic, odd number. Okay. Spice it up. What happens when we put nitrogen here? Remember, nitrogen has a lone pair. We only have 3 bonds to it. Okay. Let's draw this one out. Alright. The question we have to answer, does that structure right here have continuously overlapping p orbitals? And does that lone pair contribute to them? So I'm going to draw the p orbitals. So there are times where you do use these lone pairs. You don't use these lone pairs. In this case, since this structure stands in need of a continuously overlapping lone pair, or continuously overlapping p orbital, it's going to use this pair because it needs that continuously overlapping. So that's going to be included. We're going to count them up. We still have 6, like as before, so our 6 electrons. Three pairs. It's an odd number. It's aromatic. Alright. I'll throw you guys a curveball. We've been talking about benzene rings. What happens if we don't have a benzene ring? I'm gonna do this nicer for you guys. Here. Yeah, I mean that technically works. Let me just adjust a little bit. Here. Okay. What if we have a structure that looks like this? But there is a positive charge. What are we going to do? So, is there a ring? Yes, there is a ring. Is there continuously overlapping p orbitals? Let's see. Start with the obvious. You have these right here. Is that cation or not? Is that positive charge up there? P orbital. Yes, it is. But is it a electron? No, it's not. So I should draw some different color to represent that is not a p orbital. Well, it's not an electron, but that plus charge takes the place of it, but you do not count it as a pair of electrons. So here we got 1, 2, 3, 4 electrons. Two pairs. That is an even number. Aromatic. Alright, folks. Let's do another one. What happens if we just have that? What are we going to do? Alright. What do we got? We got this. P orbital here. P orbital here. P orbital there. What? I think, do we have a problem? Yes, we do. What is that? What's happened there? We got our ring. Yes, we do. Let's go back to our criteria. Do we got a ring? Yes. Do we have continuously overlapping p orbitals? Let's look at this. 1, 2, 3, 4. No, we're broken right here. There is not. What do we call that when there is no aromacity? Simply non-aromatic. It's neither aromatic or anti-aromatic. Watch out for those structures, they will pop up. Easy to identify. Alright, if there's a carbon without a p orbital, if there's a carbon on that ring without a p orbital, probably unaromatic. I mean, it is non-aromatic. Okay, let's try this one. And that negative charge is on the top carbon right there, as you guys can see. Alright. What do we do when there's a negative charge? So, since, unlike the positive charge, the negative charge does have a lone pair. Recall that we used that lone pair back when we had the nitrogen up in our second example. So we're going to use it because we need it to be continuously overlapping. And then let's counter electrons up. We got 1, 2, 3, 4, 5. And then 1, 2. Well, we see our 3 pairs, but we have 6 because I forgot to count our nice negative charge up there. So 6. 3 pairs that you can see because of our bond right here, bond right there, lone pair right there. 3 bonds, 6 electrons. Remember when it's odd? Aromatic. Okay. Now let's do another example. Okay, we got a nitrogen with a lone pair attached to a hydrogen. I forgot to do double bonds. Alright, I'm just gonna do circles for p orbitals now. We got 1 right there, 1 right there, 1 right there, 1 right there. Alright, it needs a lone pair like we discussed, so we're gonna use that. And now we have 1, 2, 1, 2, 3, 4, and include 2 because there's 2 electrons in here. So total of 6. And then I usually identify by counting these bonds. 1 bond, 2 bonds, a lone pair, that's 3 because there's 2 electrons in a pair. So we got 6 electrons. Three pairs. Aromatic. Okay. Two more examples. Alrighty. 1, 2, 3, 4. What about this one? We got two lone pairs. Do we need both of them? So we got 4. We identified 4 down there. And then we're going to need to use both of these. So we got 1, 2, 3, 4, 5, 6, 7, 8. Oh, my bad. That was not correct. 1, 2, 3, 4. We'll use one of them. I'm sorry. 6. We don't need both. And just as before, aromatic, odd number of pairs. So why didn't we use one of the pairs? That's because we only need one to be continuously overlapping. If it's already continuously overlapping, we don't need both pairs. If we have 2 pairs and it's not continuously overlapping yet, we use one of them. So oftentimes it may be the case where we're not going to be using both pairs. Last example. I'll try that again. Now we got 2 extras in our ring, as I'll call them. Let's get the p orbitals on the way. Okay. Well, the question is, do we use both of those? So, you see, at least we got 2 pairs down here. We need this one because or else we will not have continuously overlapping. And then let's see, we got 1, 2, 3 pairs right here. And since we have a double bond connected to this nitrogen, we do not need to use this. We're not going to be using, I'm going to circle this in red so we know not to use it. We're not using that lone pair because we have this double bond already on the nitrogen. We use the pair up here because there's no double bond connected to make a overlapping p orbital. So 6 electrons. Alright. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. No, when I say 3, I'm not counting these pairs. I'm counting double bond connection right here. 6 electrons, 3 pairs. Aromatic. Sweet. Alright. So hopefully those examples helped you a little bit to identify the difference between aromatic, anti-aromatic, and non-aromatic. If you still have questions, feel free to put in the comments, and I'll try to make a video answering them. As of now, enjoy your day, and hopefully this helped you a little bit in organic chemistry. Thank you.